What we were dealing with last day was energy like as an E equals mc delta T calculation. So just a reminder, we had this idea that delta EH for a given substance is equal to mass times heat capacity times the change in temperature for that substance. What we also said was that if we took a block of iron and we put it into water, then the iron would lose energy and the water would gain the exact same amount of energy. That's what heat exchange is. And so I'm just going to make sure we get that again. The idea delta EHI is the change in energy for iron is equal to the energy lost by iron. And if I was going to write for the water, I would say delta EH for water, W, is equal to the energy gained by water. And the context of this was that we would take a hot piece of iron, put it into water, iron would cool down, losing energy, water would warm up slightly and gain energy, right? That's it. There are other ways that people talk about that. In math speak, they say energy lost by one material is equal to the negative of the energy gained by the other material. That's the exact same thing as what I just said, but kind of in math speak, right? Or you could say, okay, well, that means that the energy lost by one material plus the energy gained by the other material adds up to zero, right? If they're the same value, but one's just the negative of the other, that's a conservation of energy. And so in our particular case, we would say the change in energy for iron, I, is equal to the change in energy, plus the change in energy for water, W, adds up to zero. That's all. That's the starting place, okay? The starting place for what we're talking about. And as I read through this scenario, I've got the mass of iron. Look, I've got a 200-gram piece of iron. I'm going to instantly turn that into kilograms. 0.2000 kilograms. Mass for water, as I keep on reading, is 300 grams. 0.3000 kilograms. And I'll go back to the iron. It started off at 350 degrees Celsius. Okay, so T1 for the iron is 350.0 degrees Celsius. And the water is 10 degrees Celsius. So cold water, colder than room temperature. If room temperature is around 23 degrees Celsius. Or 20, I don't know, somewhere in there. So find the total temperature of the closed system, T2I and T2W. Now, if I leave this iron in the water, this idea of T2I and T2W, the final temperature of iron and the final temperature of water, won't they settle down to the same temperature? Like, in other words, if I leave a hot pot that just came off the stove in a dish sink full of water, it's going to cool down to the temperature of the water. The water is going to warm up to a warmer temperature. It's going to sort of balance out, right? So what I want to say is, if I'm trying to find those two values, really what I'm trying to find is T2. This reminds me sort of what we've done with like mechanical systems too, where things kind of are moving together. In this case, it's not a system moving together, but in the end, they'll arrive at the same temperature, right? And so we kind of should know that by experience, but I'm just outlining it. Anyway, the final temperature of the water and iron will be the same at the end of the process. That's what I just said. So what we're looking for here is T2I blank and T2W blank. So those are pieces of information I don't know. And I'll make the statement formally, T2I equals T2W equals T2. That's going to be helpful in our math. More information that I might want to look up would be the heat capacity of iron and the heat capacity of water. Well, that was something that I gave you in a note previously. So 4.50. So if you're evening class, you're going to have to put that away, right? Thank you. Times 10 to the power of 2 joules per kilogram degree Celsius, and 4.18 times 10 to the power of 3 joules per kilogram degree Celsius. Remember, they're off by like an order of magnitude relative to one another. And when I say an order of magnitude, I mean a multiple of 10, a 10 to the power of. Okay? Now, how am I going to math all this out? I'm going to start off with this expression that we had here in this little preamble. Say, okay, well, delta EHI, change of energy for I, plus oops, plus the delta EHW adds up to 0. And I'm going to go from there. Delta EHI would be, I'll start over to the left here, MICI delta TI. Delta EHW would be MWCW delta TW. This is where it gets kind of annoying. Remember, if you have a delta T expression, delta T is equal to T2 minus T1. So every one of those delta T's has to expand out to a binomial. Not only that, but it's T2 and T1 for iron and T2 and T1 for water. So it's, well, let's do it. I'll start all the way over on the left. MICI times the binomial for delta TI is going to be T2I minus T1I. See how that expanded out? It's T2 minus T1, but specifically for iron. Plus MWCW, and then the delta TW ends up being T2W minus T1W. I just like saying W. Okay? And now I look at this and I think, well, shucks. I'm going to have to use distributive property because MICI is actually a coefficient out front of a binomial. MWCW is actually a coefficient out front of a binomial. I'm going to have to multiply through this thing. Sadly, that means that this thing's going to expand in a hurry, right, in terms of the math. So I get MICI T2I minus MICI T1I plus MWCW T2W minus 1. Oh, shucks, I did it again. Sorry, all this heavy language, too salty. All right, MWCW T1W equals 0. Now, thankfully, I look at this, I'm like, it's as expanded as it can get. What can I do here? Now, the name of the game, what am I trying to get? I'm trying to get T2. See that? So what I want to recognize is that T2I, remember I made this statement earlier, T2I and T2W are actually both the same value. And what that means is I can isolate that stuff. All the terms that have T2 in them, I want to leave behind on the left-hand side. I'm going to take everything else over to the right-hand side. Okay, so that's the isolation game that we're playing right now. We're going to take, I'll put a wiggly line. The two wiggly line items got to go over to the right-hand side. Let's write this out. MICI. You know what? In this slide, I'm going to ask your permission. Can I turn the T2I into just T2 now? Okay. So I'll give myself like a little instructional arrow so that when I go back to study later, I understand what the heck just happened here. T2 plus MWCW T2. Right? I'm only writing the stuff that has T2 now because the other stuff is getting taken over to the other side. Now, conveniently, notice that the terms, the wiggly terms, both have negative signs out front of them. So that's kind of cute. When they go over to the other side, they'll become positive, yeah? That's good. So I end up getting MICI T1I plus MWCW T1W. I look at the stuff on the right-hand side and I think, is there any common factors? Well, gosh, no. The temperatures are different, the heats are different, masses are different. Can't pull anything out. I look at the left-hand side. Is there anything I can factor out of this one? Come on. Yep. T2. Pull a T2 out of that guy. Leave behind MICI plus MWCW. And I want to get that T2 all by itself. So I'm going to show my work. What I would do is divide both sides by the same value, which in this case is MICI plus MWCW. Remember, you're allowed to divide by a binomial. That's fair game, right? So I get down to this expression. Oh yeah, I forgot to say, that binomial just canceled out. there. So we get down to this expression, T2 is equal to MICI T1I plus MW T1W divided by the binomial MICI plus MW. And people are like, oh, could we please cancel things out? Nope, can't do it. Would not be prudent. Can't do it. Okay? But I am at a stage where I can sub in values. Take a look at these givens. Don't I have all of them, right? We got it all. We have a wealth of knowledge, right? We can just sub this stuff in. Now, the downside is you got to write small because there's a lot of values. But we've kind of done this with pulley systems before, so we're good at it, right? It's just bookkeeping. It's just being organized. So we'll sub in our values. I'm going to drop all those extra zeros just because there won't be enough space for it otherwise. And don't get your heat capacity of iron and your heat capacity of water mixed up. Oh my goodness. T1I was 350 degrees. That's some hot iron. And the water was only 10 degrees. You see what I mean by having to write small to fit it all in. Don't forget to divide by the denominator binomial, though. And then, for your own sake, do yourself a favor. Make sure you can put the data in. Because I think that we've all messed up on these things before. The scientific notation, for some reason, messes people up. But if I can give you a tip on this one, use those brackets. They will be your best friend for data entry. Make sure that you really do have everything packaged properly when you put it into the calculator, okay? 9 times out of 10, that's the mistake. So I'll give you my answer. You guys give me the thumbs up if you can get it. So I get 32.76 degrees Celsius, and I round it off to 3 sig figs. I get 32.8 degrees Celsius. Let's see who's the quickest draw in the class. Who's got it? I see that blue calculator, like calculator of fury going over there. Can I get the thumbs up that I don't have a typo here? Does anybody have it? Or should I just trust myself this time? We got a thumbs up. Nice. All right. So we got somebody that's going to second my motion of 32.8 degrees Celsius. And I feel like Sasquatch, I will believe. Believe in myself when no one else will.